Welcome to the 8th session of our second chapter, Structure of Atom. Today, we will deal with the topic filling of orbitals in atom. How to fill the electrons in an atom we have to learn. The filling of electrons into the orbitals of different atoms takes place according to the Aufbau principle, which is based on the Pauli's exclusion principle and Hund's rule of maximum multiplicity, and of course the relative energies of the orbitals. But we have to concentrate the three rules, that is Aufbau principle, Pauli's exclusion principle and Hund's rule. Now let's talk about Aufbau principle. The word Aufbau in German means building up. The building up of orbitals means filling up of orbitals with electrons. We are filling the electrons in respective orbitals. The principle states that in the ground state of atom, the orbitals are filled in the order of their increasing energy. So it will be in an increasing order. In other words, electrons first occupy the lowest energy orbital available to them and then enter into the higher energy orbitals. Only after the lower energy orbitals are filled. So this is the main thing what we have to remember. First the lowest energy orbital is filled and then only the higher energy orbital is getting filled. The order of the orbital in increasing order is given as 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 4f, 5p, 6p, 7s. This is the order, but it's very difficult to remember this way. So that we have a diagram with which we can easily remember this order. See this diagram. This is 1s orbital. You can see the first column, it is only s. 1s, 2s, 3s, 4s, 5s, 6s, and up to 7s we have written. And this is in accordance with our periodic table. That is, we are having how many periods? 7 periods. And 18 groups are there. So that 7 periods are here in the 7 rows. Then the second line or second column is 2p, 3p, 4p, 5p, 6p, 7p. D starts with 3d, 4d, 5d, 6d, 7d. 7d is there, but we are not taking. Now 4f, 5f, 6f is there. So now how we can remember the order? You have to make a cut. That is 1s. Second line starts with 2s. 2p, 3s. 3p, 4s. 3d, 4p, 5s. We can see that the order is moving from 1s to 2s. Arrow finishes here. Third arrow starts with 2p and finishes by 3s. So arrow after 2s it moves to 2p, then 3s. Again the next arrow is starting with 3p and the cut will be 4s. The arrow finishes here. So 3s it goes with 3p, 4s, like that it moves in a way. So this pattern, if you remember, you can easily understand how the increasing order of energy is there in the orbitals. And if we remember this diagram, then it's very easy to fill up the electrons in the respective orbitals of an atom. So this way we can use the Aufbau principle. The next one is Pauli's exclusion principle. The number of electrons to be filled in various orbitals is restricted by the exclusion principle given by the Austrian scientist Wolfgang Pauli, 1926. According to this principle, no two electrons in an atom can have the set or same set of 4 quantum numbers. Pauli's exclusion principle can also be stated as only 2 electrons may exist in the same orbital, and that also in opposite spin. This we have learned while we were discussing about the difference between orbit and orbital. We said that in an orbital, maximum 2 electrons can be accommodated with opposite or pair spin. That point is from this exclusive principle. This means that no two electrons can have the same value of three quantum numbers, that is principal quantum number, azimuthal quantum number and magnetic quantum number. But they must have the opposite spin quantum number. Now let's talk about the third rule, that is Hund's rule of maximum multiplicity. This rule deals with the filling of electrons into the orbitals belonging to the same subshell. That is, when the orbitals are of equal energy are there, we say that orbitals are degenerate orbitals. And in all these orbitals, we have here s orbital, p orbital, t and f orbital. But s is having only one subshell, so we can't say that that is degenerate orbital. But p, t and f are degenerate orbitals. Why? Because p is having three subshells and which are having equal energies, px, py, pz. Same way, the d orbital is having five subshells, dxy, dyz, dxz, dx square minus y square and dz square. All are having the same energy, so they are said to be the degenerate orbital. Same way, the f orbital is having seven subshells. And we are not learning the names or the shapes, but still we can say that the f is having degenerate orbitals. So in that cases, the filling of electrons, first they have to fill what singly and then only the pairing does. This is the rule. So how the statement comes is, pairing of electrons in the orbitals belonging to the same subshell p, d and f does not take place until each orbital belonging to that subshell has got one electron each, that is singly occupied. So if the p orbital is having two electrons, we can't keep in the first subshell both the electrons. So we have to keep that one in separate subshells. Then only after filling the third subshell also with single electron, then only the pairing does. Electronic configuration of atoms. How we can write the electronic configuration. In grade 10 we have learned how to write. It is according to the orbits or according to the shells. We wrote 2, 8, 18. Like that it goes on. Right? But right now we have a different way to represent the electronic configuration in terms of orbitals. The distribution of electrons into orbitals of an atom is called its electronic configuration. The electronic configuration of different atoms can be represented in two different ways. The first one is S raised to A, P raised to B, D raised to C notation. This is the form, the first way how to represent the electronic configuration. The second one is the orbital diagram. And in this orbital diagram, we can represent the s orbital as one subshell, p 3 subshell, and d 5 subshell. So this is an example or the just introduction of these two ways. Now let's see the first notation. The subshell is represented by the respective letter symbol S, P or D. That is the orbital or subshell is there. And the number of electrons present in the subshell is depicted. We should know that how many electrons are there according to the atomic number, and we'll write as superscript like ABC. Here it is written. The similar subshell represented for different shells is differentiated by writing the principal quantum number before the respective subshell. That means if S is coming again and again, we can't write 1s or 2s again and again. So there we are representing the principal quantum number to mention the s orbital of different subshell. The second method or the notation is each orbital of the subshell is represented by a box and the electron is represented by an arrow, a positive spin and an arrow which is negative, that is plus half and minus half spin is there. So it is clockwise and anti-clockwise arrows, and the arrow represents one electron, upward half plus half and downward minus half. So this is the two notation or different way to represent the electronic configuration. The advantage of second notation over the first is that it represents all the four quantum numbers. Now, let's see the electronic configuration in first method. If hydrogen is there, we know the atomic number of hydrogen is 1. So the one electron will be present in 1s. We have to remember the Aufbau principle, and according to that diagram, we have to fill the electrons in increasing order. So the 1s orbital is there, the lowest one or the ground state one. So we have to fill the one electron in 1s 1. Then if we are having helium, it is having atomic number 2. So the 2 electrons should be in s orbital, because maximum the s orbital can accommodate 2 electrons, because only one subshell is there. So 1s2. This is the form. If it is lithium, lithium is having 3 atomic number. So the 3 electrons should be how arranged? In s orbital 2 only. So the next orbital on the increasing energy level comes for 2s. There we have to keep 1 electron. So if the configuration changes to 1s2, 2s1. If it was in the orbit, you have to write 2, 1. Next is beryllium. 4 electrons are there, 1s2, 2s2. If boron comes, there the 5 electrons are there. So we have to write 1s2, 2s2. The next one goes to 2p1. It can be px, py, pz because it is degenerate. So you just write down px or 2p1. If it is nitrogen, nitrogen is having atomic number 7. So how we will arrange? 1s2, 2s2. After 2s2, 4 electron is filled. The 3 electron should be in 2p3. But here we can't understand that which orbital is getting filled and all. But anyhow, we will do the next one. Next is oxygen. Oxygen, 8 electrons are there. So 1s2, 2s2, 2p, 4 electrons can be accommodated. So this way we can arrange the first electronic configuration. The second method, that is box diagram or orbital diagram, we can represent in this way. If for lithium we are mentioning, there lithium how many were there? 1s2 and 2s2. So 1s orbital is there with 2 electrons in opposite spin, and 2s with 1 electron in upward direction. The arrows in one upward direction. Beryllium, both the 1s and 2s are completely filled with opposite spins. So 2s2, 1s2, 2s2. Boron, 1s2, 2s2, 2p1. Carbon, when it comes, 1s2, 2s2, 2p2. Now here you can see the Hund's rule. It is obeying the Hund's rule. See the box diagram, when it is filled, degenerate orbital is there. So how we learn that when degenerate orbitals are there, it should be singly filled first and then only the pairing does. So if it is 2 electron in 2p2, we can't keep the second electron, this electron here, in opposite way. It's not the correct way. So we have to keep in the next orbit, a subshell. Like that itself, nitrogen also, when it comes, 3 electrons are there. So you can't keep in the first one 2 and then 1. You have to completely fill all the degenerate orbitals with single electron and then only pairing does. Then oxygen, when it comes, 1s2, 2s2, the 4 electrons are there. So in the first filling, how it will go? 1 electron, 2 electron, 3, and the fourth will come again here. Like that, fluorine, when it comes, 1s2, 2s2, 2p, 2p5. 2p5, how it comes? 1, 2, 3, 4, 5. Same way for neon, 10 electrons are there. 1s2, 2s2, 2p, 2p6. So all the p orbitals are, subshells are completely filled or oppositely filled. So this is a box diagram or the electronic configuration to represent. Next topic is stability of completely filled and half filled subshells. The ground state electronic configuration of the atom of an element always corresponds to the state of the lowest total electronic energy. The electronic configuration of most of the atoms follow the basic rules. However, in certain cases, like copper and chromium, where the two subshells, that is 4s and 3d, differ slightly in their energies, an electron shifts from a subshell of lower energy to a subshell of higher energy, provided such a shift results in all orbitals of the subshell of higher energy getting either completely filled or half filled. So the valence electronic configuration for chromium and copper therefore are 3d5 4s1 for chromium, 24 electrons are there for chromium. So when we write the electronic configuration 1s2 2s2 it goes on, and when we write 1s2 2s2 2p6 3s2 4p, like that, all when we write according to the Aufbau principle, 4s comes first and then 3d. But according to the D blocks, or the transition element's general outer configuration, it is n minus 1d 1 to 10 ns2. Because of that form, this configuration is written 3d5 4s1. Now here it was 4s1. It is not actually the correct one. Not actually what we are writing. The correct one is this one, 3d5 4s1, because 3d4 4s2, when we write, this is the form what we are following. But according to the stability factor, the one electron from S is shifted to 3d orbital and it becomes 3d5 half filled, and here also it is half filled because S can accommodate maximum 2 electrons, so it becomes 1 here and here it becomes 5, so both are half filled. So this is the state which is completely stable. The next one, copper, also same way. The formula or the electronic configuration when we write according to the rules, it will come 3d9 4s2. But because of the stability factor, that is completely filled and half filled cases, it changes or it shifts the one electron to 3d. So it becomes 3d10 4s1, and now 3d is completely filled and 4s is half filled. So it's again more stable than this configuration. So this is an exception case in the transition element. It has been found that there is extra stability associated with these electronic configurations. The next topic is causes of stability of completely filled and half filled subshells. The completely filled and half filled subshells are stable due to the following reason, that is symmetrical distribution of electrons and exchange energy. These are the two things which causes the stability of completely filled and half filled subshells. So this is our last topic of the chapter. With this we are concluding our chapter 2, structure of atom. Hope you understood the chapter very well. Thank you. We'll continue in the next session.